We saw this slide last time. So one of the things, we have a state variable, such as pressure is just a variable for us, temperature is just a variable for us. If we have a combination of variables related through some equation, we would call it a function, just sort of y equals mx plus b is some function. So we can also have state functions, okay? So enter the new stuff. Internal energy, which remember we have a lot of ways to define it, such as our most important one here, we'll write it as heat plus work. It's a function, it's a state function, okay? And so what that means is that if we consider a system that's at position A, it's at some pressure volume, it's also at some temp, it has some other macro properties about it. And it travels along a path, and I don't really care what the path looks like, but it travels over to some new position B. There was a change in energy, internal energy that occurred. But if I go back now, I go back along a different path, doesn't matter what path I took, and I go back to A, internal energy has to go back to being the same. If it doesn't, I've created or destroyed energy and I'm defying the first law of thermo. So consider a system that goes from state A to state B, then goes back along a different path from B to A. If the internal energy changes by delta U in going from A to B, so there's some change, delta U changes, this has UA, this has UB, and UB minus UA is equal to delta U, then it has to change by negative delta U on the reverse trip, otherwise it will result in a non-zero change in energy of the system, which we can't have. Since U depends on the endpoints, in this case A and B, we say it's a state function. So if something depends only on the endpoints, we can call it a state function, and for example, internal energy is one for us. Okay. So the opposite of this, or an alternative to this, and I've sort of alluded to the only other two options we have, are path functions or process functions. Okay, and so these, path matters. Okay. So now consider the work being done by this system or on the system as you go between the two states, A and B, along the two different paths, 1 and 2. So if you go from A to B along path 1 here, the work done is the area under the curve on our PV diagram. But when you go back from B to A along path 2, there's more work here, there's more area under the curve, and this green area represents the difference between those two. Okay? Recall that work is the integral of the area under the curve, or PDV. So here we can see that work does depend on path. We can call it a path function. And so it's easy to kind of think of it here because you can compare the size of the areas here and kind of convince yourself that yes, work depends on path. It's a little bit harder with heat to convince yourself, maybe, other than I told you it has to flow. But if you look at the first law, it kind of works in that going from A to B and then back to B to A, this has to be 0. I just told you this is definitively non-zero. Thus, this is also non-zero. Is kind of my way to think through it. And on the next slide, I have that repeated, right? So if you kind of think through it, change in internal energy going from A to B and then back to A, regardless of whatever, if you're taking two different paths, this is going to be equal to 0. So if you just rearrange it, heat also has to be a path function.